Hello, everyone. I'm Andrew Haselton, mechanical engineering student at the University of Alabama. This summer, I've been working with Dr. Engelberg in the biorobotics lab on the design optimization of soft robotic jellyfish. Soft robots have a distinct advantage when operating around fragile marine environments like coral reef. Imagine a robot made out of metal that happens to collide with the coral reef. The robot's not going to be able to absorb any of the energy of the collision, and so it's going to all transfer into the coral reef and probably damage it in one way or another. Compare that to a soft robot where it's able to flex and comply. If that has that same sort of collision with the coral reef, the robot's going to be able to absorb a good chunk of that energy and reduce the odds of damaging the coral reef. And so this is something that Dr. Engelberg's lab has worked on before. You can see in the bottom left, the previous iteration of the jellyfish. It worked. It was able to navigate, but it was a bit inefficient in its motion and presented the opportunity to improve it and also move closer to emulating a real jellyfish. And so these robots would be able to be a bit of a research on themselves in terms of underwater locomotion and soft actuators, but would also importantly enable additional research by being able to get sensors or cameras up close to a coral reef, closer than you'd be comfortable doing with a robot that has a higher chance of damaging it. And so my objectives this summer were to improve the jellyfish design for greater propulsion, to optimize the actuation pattern once I have that design, and then evaluate the impact that the bell could have on propulsion to move closer to a real jellyfish. Some of the primary challenges I had were that all the molded components, the actuators, the bell, all that, those take significant time to produce. You have to spend maybe half an hour mixing and pouring the resin, wait upwards of 4 hours for it to cure, plus whatever time it takes to design and print the molds, which means it's really a challenge to iterate some of these components, especially the actuators, of which there's 9 in total. And the initial bell design ended up being quite difficult for the actuators to manipulate, so I had to pivot to an alternate design. And so the design improvements I was able to make were reorienting the actuators. The actuators were previously in a naturally horizontal configuration. You can see in the lower left on the previous design, I reoriented them to be in a vertical configuration. So that instead of going down when they actuate, they would kind of go outwards instead. I also improved the retention of the actuators to the jellyfish, which helps ensure they stay in place during collisions, which, considering this jellyfish is designed so that if it collides, it's not harmful, that's definitely something to keep in mind. And then I was able to add a bell to increase the effective surface area of the actuators. And so talking about these bell concepts, it's important to consider how a real jellyfish is able to move. It manipulates that outer layer, the bell, to control the water inside of it. It doesn't use like any sort of propeller, and it doesn't really do a flapping motion either. So that's something I wanted to emulate. First design was a single piece EcoFlex bell. This was just basically a tube made out of EcoFlex, which is the flexible material. The issue this had is that when the actuators all turned on, they would expand outwards, and expanding the lower circle of the bell was really difficult, something they weren't strong enough to do. And so what would happen is they would just curl up rather than actually expand and contract the bell properly. So I decided, okay, how can I remove that effective spring around the entire thing? So my first idea with that was the 9-piece hinged bell. And this worked by having a flap in front of each actuator, which would help increase the surface area of the actuator effectively, while not having the problem of all the actuators having to fight against one giant spring. But the issue with this is that as the flaps would expand, there'd be gaps between each of the segments. And so when it was fully expanded, you'd have more gap than actual flap in there. So you'd be losing a lot of potential, and you wouldn't be able to get as much surface area as you could. And so the compromise between those was a 3-piece bell. The actuators are in groups of 3, each of which is controlled by its own pump. And so by putting a segment of the bell in front of each of those, I could minimize the gaps by reducing it from 9 gaps to 3 gaps, while also maintaining the aspect of it being a bell and not having the issue with having to expand the whole thing. 3 individual segments meant that you didn't have to expand the entire diameter of the bottom, but you could work on just expanding a smaller portion of it. And so to fabricate the bell, I 3D printed a mold and then would insert the ribs inside of it. These ribs serve to control the motion and shape of the bell. Imagine just having a just just the EcoFlex material. It's just a limp fabric, and especially in water, it would float around. It wouldn't be able to hold any shape. It wouldn't be able to return to its natural position. So these ribs give me the ability to control the flex of it and constrain it relatively to going inwards and outwards. They don't like to flex to the side as much. And so these ribs would be suspended inside the mold. The EcoFlex would be poured around it. And then you end up with one of the bell segments, which is able to hold its shape pretty well, especially when it's attached to the jellyfish itself. And so I got these segments created and I hooked it up to our test sub. At the top of above the tank, we have a load cell, which is able to measure the thrust of the jellyfish. And this load cell is hooked up to the amplifier board in the lower left, which just amplifies its signal and then feeds it through a National Instruments DAC into our Simulink model to log the data after passing it through a low pass filter to take out any noise. The actuators are controlled by the Simulink model as well, which feeds into the actuator control board in the center of the screen. And that just takes the signal, then uses a few transistors to turn the pumps on and off. And so you can see a sample of the pump control signal in the top left at the top of that graph, just on and off and on and off. And then the load cell reading a sample of that below it. And this setup allowed us to change the actuation control really easily and streamline the testing. So here's the jellyfish in action. Oh, okay, that video doesn't seem to be working. But I can somewhat show you here is that you'd have the actuators going out and the bell would expand outwards and then it would naturally return inwards when the actuators go back down. And so to test the jellyfish, I had to come up with the testing parameters. And so I characterized the control signal in terms of the interperiod interval, or IPI, which is just the overall period of the signal, the distance from the peak to the peak, and the pulse width, which is just how long the pump is on for each cycle. So I tested an IPI range of 2 seconds to 7 seconds, and the pulse width ranging from 1 second to 2.6 seconds. You notice in the chart on the lower right that the lower left and top right of the grid aren't actually being tested. And that's because on the lower left, you have a really high pulse width compared to the period of the signal, which could lead to the actuators not having enough time to drain and contract and could lead to them rupturing. While on the top right, you have so little actuator on time compared to the period that all you're changing is whether you're having the actuator rest in its natural position for 1 second or 2 seconds, which really just doesn't have much value and wouldn't be able to positively impact the propulsion at all. And so as a baseline, I wanted to test the jellyfish without the bell, just the bare actuators. It produced backwards negative thrust. While this could lead you to propelling it, the goal was to be able to put some sort of sensors or camera inside top dome. And being able to lead with that would be very advantageous so that you're not having to basically back into everything that you're trying to look at. And these results were evaluated by integrating the force with respect to time after subtracting a baseline value for the weight of the jellyfish. Noting that on the load cell graph, positive thrust is down. And while that peak is a bit larger in terms of amplitude, as you can see, it's shorter in time. And so the reverse thrust that's above the red line is actually more area in total. And that means that you're producing net negative thrust despite the larger peak. Now, compared to the improved result with the 3-piece bell, this did achieve positive propulsion. Maximum propulsion was achieved at an IPI of 6 seconds with a 2-second pulse width. And you can see that compared to the previous slide, the width of the spike below the graph on the load cell signal is a lot wider. And so there's a lot more area over it. It's able to sustain that positive thrust segment for a lot longer, to the point where it's able to cancel out negative thrust at the start of each cycle. And you can see the overall results in the lower left of that. Some of the IPI and pulse width combinations didn't produce positive thrust. Some produced a little, but really it was 6-second IPI and a 2-second pulse width that produced optimal results, with a fairly close second place at actually a 3.5 second pulse width, 3.5 second IPI and a 2-second pulse width. And so I just like to show the comparison of CAD to reality, and you can see how in the top part of the jellyfish, there's a lot of room for any sort of control electronics, any sort of sensors, and this would allow the jellyfish to be used for possible research in and around coral reefs in the future, which was really the goal, to be able to enable that sort of thing. And then, so I'd just like to thank, Dr. Engelberg for this. Diego in the lab also provided a lot of help with the electronics side, and of course, everyone here at the REU.